Okay, so main carbon chain, we found the longest chain, which is 6 carbons long. And they will do this to you on the test. They will give you a structure that looks like this, that looks like, oh, it's 5 carbons in a row with an ethyl group on it. No, you have to double check. They will. I've seen it multiple times in question bank that they do this to you. So we have 3 substituent groups. What kind of groups are they? Methyl groups, yes. 1 carbon, CH3 is a methyl group. So we have 3 different methyl groups. How are we going to number the main carbon chain? From left to right or from right to left? Left to right, why? Yes. What we want is the sum of the numbers of the substituent groups should be as small as possible. So if we number it like this, where it's 1, 2, 3, 4, 5, 6, we have 2 methyl groups coming off of carbon 2 and 1 coming off of carbon 4. If we did it the other way, it would be 3, 5, and 5. So we want smaller numbers, so we're going to call this 2, 2, 4. Those are the numbers. We're grouping them all together because they're all methyl groups. They're all the same thing. So we're going to go 2, 2, 4. And then what's the next part? Trimethyl. Hello. And then how do I name the root? Hexane. So we've got 6 carbons. That makes it a hexane. It's ane because it's just an alkane. There's no other functional groups on there. If there was a double bond in here, it would be an ene. If there was a triple bond, it would be an ine with a Y. If there was an alcohol, it would be hexanol. So it would actually hexane dash the number of the carbon dash all. I'm not going to go into a lot of that. If you want to practice naming different compounds in your study guide, there are all those pages that just have a whole bunch of structures on them, and they talk about the different classes and they give examples. In the answer key for the study guide, which I believe I've already posted, those are all named. So you can check your own naming with that. And then the packet that I gave you, the Introduction to Organic Nomenclature, that is just alkanes, alkenes, and halogenoalkanes, so it's kind of keeps it simpler for you to practice this process. You don't have to do the whole packet. Obviously, if you're testing and you're struggling with this, you might want to do as much of it as you can. I'm sorry that I haven't put the key for that up yet. I will do that tonight. And so, but I do want like the equivalent of 3 pages of that packet done as a practice prep. All right. Senior interims are tomorrow. I'm going to put a grade in, and I will give you back your periodicity and bonding tests tomorrow. My parting gift to seniors is that I will, because you're running out of time, we are running out of time collectively, and so much of this is test-driven. You may, by the end of your term, the 26th, write corrections on one of your take-home tests. So normally you don't get to write corrections on take-home tests, but if one of them brought your grade down significantly, you can choose to write corrections on that to bring it up. So seniors only. Everybody else, you'll have some more opportunities to boost your grade. Okay. So what I'm going to leave the nomenclature behind now. Well, for the most part, we'll name these just for practice. But what I want to start talking about are a couple of other things about the structures that you need to know, a couple of other sort of terms that you need to know about the structures of these organic compounds, and then start talking about the reactions, because that's really the last bit of the topic is the different types of reactions of different compounds. So we'll do that today and into tomorrow. And then Wednesday, I will start talking about option D, which is the medicinal chemistry. And also be throwing in topic 11.3, the spectroscopy, because those are both intimately involved in the organic chemistry. So, and topics 8 and 9, do your best. Sorry. Okay, so page 17 in your study guide talks about structural isomers. Structural isomers are where we have the exact same molecular formula, but completely different molecules. Not completely different, but, fairly different. So this is pentane. This is also known as N-pentane, because this is an unbranched, complete straight chain, just 5 carbons in a row. So the N, I forget what it's actually supposed to stand for. I always think of it as normal pentane, like just the straight chain, okay? But the same, there are 2 molecules with exactly the same molecular formula, exactly the same number of atoms of different elements, but with different structures. So here we've got a branch on a 4-carbon chain. So this would be 2-methyl-butane. And then this is going to be 2 branches, 2 methyl groups branched off of a 3-carbon chain. So this would be 2,2-dimethyl-propane. Now you might say these aren't that different from each other, and you'd be right. There's not like a different functional group going on here. They're all alkanes. They're all totally nonpolar molecules. They're all the same, exact same molecular weight. But they are going to have some different properties. Any ideas what a property might be that would differ among these 3 structural isomers? Some type of physical or chemical property that might be different. Jacob. Melting point or boiling point? We usually talk about boiling point with organic molecules because for the small ones at least, they tend to be liquid or gas. But yeah, boiling point. So who's going to have the highest boiling point? For which one is it going to take the most energy to separate the molecules apart? Yeah. Nope. It's going to be the N-pentane. Yes. I appreciate you speaking up. This is going to be the highest boiling point. And this one is going to be the lowest boiling point. But why? It's a great question. Nick? Okay. Okay, so what does that have to do with boiling point? So we have 1, 2, 3, 4, 1, 2, 3, 4 carbon-carbon bonds. We have exactly the same number of bonds in both molecules. Is it 5? 1, 2, 3, 4. 1, 2, 3, 4. So it's not the bonds. You're on the right track, though. Jacob? Yes. It's about the London dispersion forces, the intermolecular forces. Boiling point and melting point are very strongly determined by the intermolecular forces in organic compounds. Okay? In ionic compounds, it has to do with the forces of attraction and the size and charge on the ions. But in molecular compounds, of which organic molecules are all molecular compounds, it's all about the intermolecular forces. How much are they going to want to stick together? So, N-pentane, these molecules are going to want to stick together more. They're going to have a higher probability of sticking together at any given point in time because the dispersion forces have to do with the random movement of electrons. And if we have a long stretched out molecule, there's a higher probability that one end of the molecule will be slightly negative or slightly positive at any given time, given the random movement of electrons, than if we have essentially a spherical molecule, where if there's a little bit of an electron distribution difference, it's not going to be stretched out as far away from sort of the center of the molecule. there's less likely to be that temporary dipole. It's not likely to last as long. So that instantaneous temporary dipole is going to be more likely and stronger in the long stretched out molecule than it is in the spherical molecule. Okay. All right, so that's an important thing about structure. If you look further down on the page, you've got a couple of examples of two molecules, again, with exactly the same molecular formula, but very different structures. What would you call the class of molecules that the first structure belongs to? It's a carboxylic acid, yep. It's got the double bond O and the OH, the carbonyl and hydroxyl, which makes this a carboxyl group. So this is going to be a carboxylic acid. And what is this molecule going to be? Nope. Good guess, though. Close. It's an ester, yep. So it's got another oxygen there, yeah. Okay. All right, so again, exactly the same molecular formula, two completely different classes of molecule with different properties. This is why we don't really use molecular formulas very much in organic chemistry, because they're kind of useless, because it doesn't really give you that much information, unless all you're trying to do is calculate the molecular weight. Okay. All right, one more structural thing. When we are talking about the position of a substituent group on a carbon chain, it can be, and it's usually the alcohols and the halogenoalkanes that we talk about in this way, because they're the ones that can kind of be anywhere, right? They can be in the middle, they can be on the end, they can be in any place replacing a hydrogen, no matter what. Okay? So we classify them as primary, secondary, or tertiary, depending on where they are. Depending on how many carbon atoms are bonded to the carbon atom that's bonded to the functional group. That's a lot of words. Basically, you look at, okay, here's the alcohol, here's the carbon that's bonded to. In each case, I'm circling the carbon that the hydroxyl group is bonded to, okay? And you can see that this carbon has one carbon attached to it. This carbon has two carbons attached to it, and this carbon has three carbons attached to it. So this is primary, secondary, tertiary. I should have asked Wiley to explain this, but you substitute a chlorine, bromine, or iodine for the alcohols, and that's essentially what Wiley was looking at in his IA. Okay. Questions on these structural terms? All right. We're doing the flyby version of this, so there's a lot more stuff that we could go into. I recommend that you go through the study guide, that you go through the answer key for the study guide, that you go through the textbook or in thinking or whatever. That is whatever is most useful to you. Leah, do you happen to have those notes? Was it you or was it Kirsten who had the notes? For your math? Do you have those? So Leah was just talking the other day about how she was studying for her calc test. And this is exactly what I was talking about when I was saying, like, make your own study guide. So, I mean, you don't have to be, colorful about it, but, she's gone through each section of something that she needs to know, drawn the diagrams, written down the important words, used colors, used arrows, flowcharts. This is the kind of thing that If you're like, what do you mean make your own study guide? This is the kind of thing that I'm talking about. Again, it doesn't have to be this beautiful, but just the idea of how are you going to organize your thoughts, your the things that you need to know, the terms you need to know, the diagrams you need to know. This is a really useful way to study. And it's not the same as just copying your notes down from before. It's really the choice of what to put in that study guide, of how to express it, of which diagrams are the most important. All of that decision making is studying. So the process is the studying. And what you come out with just, might be something very useful to just kind of page through the day before the quiz or the test, but that's what I'm talking about. Okay, moving on. We're flipping in our study guides all the way to page 26, where we are starting to talk about different types of reactions. There are several different reaction types, or several different classes that you have to know at least a couple of reaction types for. And so we're just going to march through those, basically. And we're starting out, though, with what happens when we separate two atoms, two bonded atoms. Because a lot of the time, all of the time, that's what's happening, right? That's what's happening when we have a chemical reaction, is we're breaking bonds, forming new ones. And there are different ways that we can break bonds in organic chemistry, in all chemistry, but you specifically have to understand these two types of bond breaking for the purposes of understanding the different types of organic reactions. So, homolytic and heterolytic. Just like with homogeneous and heterogeneous mixtures, or homozygotic and heterozygotic. In biology, homo means same, and hetero means different. Okay? So, in a homolytic fission, both atoms end up with the same number of electrons from the bond. So, the chemical bond is, in the case of a single bond, is 2 electrons that are shared. When we have homolytic fission, each atom takes 1. And this creates what we call free radicals. Okay? These are unpaired electrons. They don't want to stay this way. Okay? But this is often the first step in a series of reaction steps that we'll talk about later. So when people talk about free radicals and antioxidants and things like that, this is what they're talking about. Getting rid of stuff like this is important because things like this can react with all kinds of stuff. They're very reactive and they can, do damage to your cells if we're talking about a biology perspective. And so you generally want to avoid making free radicals or having a lot of free radicals floating around in your body and your cells. But it is important in a lot of reactions for this to be an intermediate step, to create these free radicals, these unpaired electrons. In heterolytic fission, then what ends up happening is ion formation. And this is where one atom ends up taking both electrons, generally the more electronegative atom. So for example, when a carboxylic acid loses a proton, loses that hydrogen off of the OH, that's a form of heterolytic fission, where the hydrogen waltzes away and the oxygen keeps both electrons. The resulting conjugate base is negatively charged, and the hydrogen is positively charged. Okay. So just knowing homo and heterolytic, what that means. Lysis means cutting. So we talk about hydrolysis. It's when you take water and you stick it into a molecule and it causes bonds to break. I don't think we're going to talk about that in this topic, but I can't remember if we're going to talk about it when we get to the option stuff. It's definitely an option A, or B, the biochemistry. So, lytic, to lyse something is to cut it. So homolytic means cutting equally. Heterolytic means cutting unequally. Okay, now we start talking about different classes. So this is the next page in your study guide. The alkanes are boring, okay? They don't do much. They don't react much by themselves. You can't really use them for a whole lot of different things, okay? Because they're already, the bonds are pretty strong, and they're nonpolar. So nothing is going to be wanting to come in and grab a hydrogen or attack the carbon or anything like that. These nonpolar bonds are pretty stable, and the bond enthalpies are fairly high, 300, 400 kilojoules per mole. So there's really only two types of reactions that you need to know that involve alkanes. One of them is combustion. This is something you have to be able to write a general combustion reaction for any given alkane, and then also balance it. That's a frequent, I've seen it multiple times in paper 2. You know, write the equation for the combustion of butane or propane or whatever it happens to be. A combustion reaction is always has the alkane and oxygen as reactants, oxygen as in the form of O2 because it's diatomic, and then carbon dioxide and water as the products, always. So if it says complete combustion, or if it just says combustion reaction, it doesn't specify, this is what you're writing. You're writing whatever the organic compound is plus O2 yields CO2 and H2O. And then you'll probably be asked to balance that equation. Yes? If it were complete combustion, yes. Yes. And if the gasoline was pure hydrocarbon, then yes. But there's other things going on in your combustion engine. So there's nitrogen in the air as well as the oxygen. That also gets, and there are sulfur compounds, usually in impurities in the gasoline or a part of the gasoline that also get involved in the reactions that are happening. So you end up with incomplete combustion, first of all, and then also a whole bunch of other products, which then your catalytic converter has to try to remove before it comes out of your vehicle. Speaking of which, there is incomplete combustion if you don't have enough oxygen. So people who, like my nephew, who work on internal combustion engines, one of the things they have to do is carefully calibrate how much oxygen goes into the engine, because you want to get as complete combustion as possible. That's going to give you the best bang for your buck, and it's going to give you the least products that you don't want. So the reason that you never, ever, ever, ever want to be sitting in your car or running your car in a closed garage for long periods of time is because there will be incomplete combustion in your car engine, and it will produce carbon monoxide, which will kill you. So please don't ever, ever, ever run your car for long periods of time in a closed space like your house garage. What? I am not going to answer that question. Don't do it. Please don't die. Please don't die. Okay, let's just go with that. Okay. Just open the garage door. I don't care how cold it is. Open the garage door if you're going to run the car. Okay. Phew. Okay. So carbon monoxide is a frequent product of incomplete combustion. So you will also need to show carbon monoxide and okay? and water instead of carbon dioxide. Again, if you don't have enough oxygen, you can't make carbon dioxide. That's too many oxygens. So you make carbon monoxide instead. If you really don't have enough oxygen, then you start just making solid carbon, and that's really bad for your automobile engine to have like carbon deposits all over the place. So that's another reason why it's very important to have good air intake, oxygen intake into your internal combustion engine. So you need to be able to write all three of these possible products of combustion. So the main one is just carbon dioxide and water. In all cases, it's your alkane or your hydrocarbon and O2 as your reactants. The products depend on whether we're talking about complete combustion, which is always CO2 and water. That's what we taught you in Honors Chem. And then incomplete combustion can be carbon monoxide or just carbon because it doesn't have enough oxygen to make the CO2. And then obviously balancing them will be a little bit different depending on which one it is. Okay. And this is just an example for C3H8. It could give you anything. They won't give you some like gigantic, molecule, but I don't think they'll go past 10. Okay, so combustion is one of the main things that you'll be required to know about things that you can do with alkanes. I mean, that is the methane that we burn in the Bunsen burners. That is the propane that you burn in your gas grill, the butane that you burn in a butane lighter, and then the gasoline that you burn in your car. And then you can also have what's called a free radical substitution. And this is a 3-step process. And this is, the substitution means like substituting one thing for another. So basically what's going to end up happening is we're substituting, in this case, a halogen for a hydrogen in your organic molecule. So the way that works is by first the creation of a free radical, which is going to be homolytic fission, right? Homolytic bond breaking. And this often happens generally needs some kind of energy input, which in the case that you're required to know is UV light. So this is what's happening to the chlorine. One of the things that's happening to the chlorine in your swimming pool outside when the sun is shining is you're getting homolytic fission of the chlorine molecules into free radical single chlorine atoms. These really do not want to hang around. They really want to react with something else. So if these are around and they come into contact with an alkane, like methane, then what will happen is, first of all, after the initiation of just the creation of the free radical, the propagation happens where the free radical gets transferred to the methane molecule, and the chlorine basically steals a hydrogen from the methane. So one of these hydrogens goes onto the chlorine to make HCl. Now the chlorine is safe. It's no longer a free radical. It's bonded with something. But now the methane has the free radical. And if there's more chlorine around, it's going to attack one of these chlorine molecules to get rid of its own unpaired electron. It's going to take one of the chlorines to make this chloroalkane, and then the chlorine that's left behind, it's going to, plus one of the electrons of the bond, the chlorine that's left behind is going to have a free radical again. And guess what? This is just going to keep going back and forth. It's a cycle. Hence the term propagation. So if we have a bunch of methane and a bunch of chlorine together, once it gets started, once the UV light starts creating some free radicals, then the reaction propagates. For as long as there's still as long as there's still chlorine, as long as there's still methane for the chlorine free radical to attack, and as long as there's still chlorine molecules for the methane free radicals to attack, or the methyl, I guess, free radicals to attack, it's just going to keep going over and over and over and over again. Okay. And then termination. At some point, there are going to be enough of the free radicals to get them together to form to reform compounds. Either the free radical chlorines coming together to remake a Cl2 molecule, or the free radical methyls to come together to make an ethane. Or a free radical methyl group tagging up with a free radical chlorine atom, as opposed to attacking a Cl2. If it meets up with a free radical chlorine, then we're going to make methyl chloride, right? Or chloromethane, I should say. Okay. So what ends up happening, though, what we write for the reaction, this is the most common sort of product of the termination step. This doesn't happen as much, as often. It's going to depend probably on the proportions of the stuff that's in the mix. But this is the main outcome. And so when we write the equation, we're saying that we've got methane and chlorine, the diatomic chlorine molecule, in the presence of UV light. We're going to end up with some chloromethane and HCl, hydrochloric acid. Okay. So at some, in the middle, in the beginning, we've got a lot of chlorine hanging around that's available to make radicals. In the middle, we've got kind of a mix of methane, chlorine, and the free radical versions of both to keep this cycle going. And then towards the end, when we start having enough stuff around that the CH3Cl is pretty prevalent, and these chlorines and these chlorine-free radicals and these methyl-free radicals have nowhere else to go, that's when they end up making these various substances and ending the cycle, coming out of the cycle. All right, so since each round of the cycle makes the CH3Cl, and since the CH3Cl is also an possible end product, that's why that ends up being the main product that we write in the summary of the reaction. That's a lot. Yeah. So we initiate, make free radicals. We propagate through transferring the free radicals between the methanes and the chlorines, and then we terminate by putting two free radicals together. And what we end up with is, because of the cyclical part, every time the cycle goes through, we end up with a CH3Cl and an HCl. Those are our main products of the reaction. This was, I believe, it's, this cycle is, I've seen a couple of paper 2 questions about this cycle, so. Yeah. Questions? Okay. Recording's still going. Mic's still on. Okay. All right, so those are the alkanes. Those are the only things that can happen, that you need to know about, that can happen to the alkanes. They can either burn up, or they can undergo this kind of halogen substitution with the free radical chain. All right, alkenes. Things with a double bond. They are much more likely to react with stuff because they've got this extra pair of electrons kind of floating around. Not really floating around, it's a bond between the two carbons, but that creates a lot more possibilities for things to happen than when we have what's called a saturated alkane. So alkanes, let me go back. I'll just write only single bonds between carbons. So alkanes are called saturated hydrocarbons because there are no double bonds. An unsaturated hydrocarbon would be something that has a double bond. Okay? You've heard this mostly in the context of fats, saturated fats, unsaturated fats. Saturated fats tend to be solid because they can make these nice layered structures with these nice straight chains, whereas unsaturated fats tend to have kinks in the carbon chain, and so they tend to be more liquid at room temperature. Anyway, our double bond can undergo a number of possible reactions. So first of all, it can be hydrogenated, meaning we can just break the double bond and add 2 hydrogens to make it into an alkane. Okay. Nickel isn't the only catalyst you can use, but it is one of the common ones. So you tend to heat this up, throw in some hydrogen gas under pressure, and have a catalyst in there. You plop in some alkenes, and you come out with some alkanes. It's pretty cool. We can also, instead of hydrogenating, we can halogenate. We can add a halogen molecule and end up breaking that bond and adding 2 of the halogen atoms instead. So if I have an alkene reacting with Br2, then I'm going to break that double bond and add 2 bromines. You can do this with any of the halogens. You can also do a reaction where you add 1 hydrogen and 1 halogen, typically in the case of these hydrogen halides, which are also essentially acids. So hydrobromic acid added to an alkene is going to create a bromoalkane. And same thing with carbon or with chlorine or with iodine. So basically, we're just taking out that double bond and replacing it with 2 other bonds to make an alkane that has either hydrogen or halogens or one of each in lieu of the double bond. They can also make alcohols if they are reacting with water. And the sulfuric acid is a catalyst. It creates, as you know, it creates a different kind of route for the reaction to take place. But essentially, we end up putting a hydrogen on one of the carbons and an OH on the other carbon, and we end up with an alcohol. So the alkenes are really like the workhorses of organic chemistry. We can make all kinds of things by taking an alkene and sticking whatever we want onto those carbons instead of the double bond. I mean, within reason. Okay. And that is where I wanted to leave it today. That's a lot to take in. So we'll continue a few other reactions tomorrow. Any questions from today's stuff? Other than all of the questions about today's stuff? Yeah.